Hello everyone, myself Anurag Dubey and welcome to this project demonstration on UART based character transmission and reception between C program and FPGA for LCD display. In this video, we will explore how a C program running on a PC communicate with an FPGA via UART and displays received characters on an LCD screen. The goal of this project is to design and implement a system where a C program on a PC sends characters using UART. An FPGA receives and processes the data in real time. The received character is displayed on an LCD screen connected to the FPGA. Additionally, the system provides an acknowledgement for received data. So let's start. Before diving into the UART-based character transmission and reception project, let's first go over the necessary prerequisites. Understanding this topic will help in successfully designing, implementing, and testing the system. First one is UART protocol. So first we need a basic understanding of UART protocol. Know how UART enables serial communication between devices. Knowledge of baud rate, serial communication, and UART data frame is a plus point. Next one is Verilog SDL. So next we need familiarity with Verilog hardware description language, ability to design and simulate digital circuits, and some experience in writing and verifying Verilog code. Next one is C programming. Since our project involves a C program transmitting data to an FPGA, knowledge of C is essential. Understanding basic syntax and program structure in C is a plus one. And next one is Vivado EDA tool. Finally, we must be comfortable using the Xilinx Vivado EDA tool, creating and managing the FPGA project in Vivado, and synthesizing and implementing FPGA design, including the UART receiving module. Now we will walk through the workflow of our project, highlighting how data flow between the PC and FPGA to be displayed on LCD. So first step is data transmission from the PC. The process begins with a C program running on the PC. This program generates a character or a string that we need to transmit via UART. The data is sent through a serial interface to a driver which handles communication over USB. And inside Vivado, we have a UART receiver module and pin mapping configured for FPGA communication. After that, there is USB UART converter. The data is transmitted via USB and goes through FT2232 chip. This chip converts USB signal into UART serial communication. It ensures the data is correctly transmitted and received by the FPGA. Now the next step is data processing in the FPGA. Once the FPGA receives the serial data, the UART receiver inside the FPGA decodes the incoming character that we are sending via the C program. The received data can be processed and used for display. Additionally, the FPGA can send acknowledgement signal back to the PC if needed. Now last step is displaying data or character on LCD. After processing, the received data is sent for LCD display. The LCD connected to the FPGA board. Here the FPGA board is SPARTAN 7. It displays the received character in real time. So this ensures successful data transmission and reception. This pictorial representation visually explains the UART-based FPGA communication workflow. A character, for example A, is sent from a C program running on a PC via UART. The data is transmitted using a USB to serial interface. The FPGA receives the character and processes it through the UART receiver module. The processed data is forwarded to the LCD module for display. The LCD successfully displays the received character. Here the received character is A, confirming end-to-end UART communication. So this confirms real-time data transmission from PC to the FPGA and then to the LCD. Now we will see our project development stages. Our project development stages is broadly classified into three parts. Here is a quick review. The first part is UART receiver design and verification. Here we will implement the UART receiver in Verilog and test it using a test bench in Vivado to ensure correctness. Next stage is C program for UART transmission. Under this stage, We will write a C program to transmit data via UART and verify the correct data transmission to the FPGA. And the final stage is the implementation and display on LCD. Here, mapping of FPGA pin for UART and LCD connectivity will be done, implementing the LCD controller in Verilog, and after that displaying the received character on the LCD. So it ensures efficient debugging and verification at each stage. So the stage 1 of our project development is UART receiver design and verification. Here we will cover the key component of our design. After that we will see the block diagrams and timing diagrams. After that we will verify our design and implement our design through the Verilog code. So let's start. So UART receiver consists of key components that ensure accurate and efficient data reception from a serial communication channel. So some of the key components of our design are baud rate synchronization. So receiver must synchronize with the transmitter baud rate to correctly sample the incoming data. As you don't use any clock, so baud rate synchronization is necessary. Otherwise, the correct bit cannot be received. Next is state machine for data reception. A finite state machine controls the reception process. Next is shift register for data storage. Basically, UART is a serial communication. So a shift register is required that stores the incoming bit until a complete byte is received. And data is shifted in one bit at a time based on the baud rate clock. Next is bit and sample counters for timing control. So bit counter counts the number of bit received, and sample counter will ensure correct sampling within each bit period to improve reliability. So basically sample counter ensures when should be the sampling of the data is to be done. Next is synchronous reset and data assign. A synchronous reset will ensure all the registers and counters initialize properly. Basically through reset, we implement the initialization, and once a byte is received and verified, it is stored in a data register for further processing. So these are the key components that we have to implement in our design. And for verification, it undergoes a rigorous verification process using a simulation tool. So the key component of verification is clock generation, and the frequency of clock will be the same as the FPGA clock that we are using. Your transmission task. So basically, we will create a test bench task that mimics the UART transmitter sending data to the receiver, which is a test data. This helps validate correct data reception and error handling. After that, file-based input for testing. So basically, for verification, I am sending file-based input. You can do with any other method. After that, simulation control. Next is real-time monitoring and debugging. Real-time monitoring of the received bit will be done to ensure the correctness of our design. Next, we will see the block diagrams and timing diagrams of our design. The UART receiver module consists of clock, reset, and RX data as the input signal. Clock provides the timing reference for the receiver logic. Reset basically resets the receiver to an initial state and clearing all registers. And RxD, which is a received data line, it is a serial data input that receive bit from the transmitter. And in the output side, we have 7 down to 0 RX data. It is basically 8-bit output that hold the received data byte. And we have valid RX, which is a signal that indicates when the valid data byte has been received successfully. Now the module wait for the incoming serial data on RxD. And when the start bit is detected, it begins capturing the next 8 data bus. Basically, we have a register of 10 bit, out of which the first one is start bit, and as we can say from the data frame format, the first one is start bit and last one is stop bit. In between, we have a parity bit also, which is optional. In my code, I am not using parity, but you can use. So it is basically consist of 10 bit. So first one is start bit. So when I start bit, it is a low signal is detected. It begins capturing the next 8 data. These 8 data. So the received bits are shifted into a register. So these received bits are shifted into a register, and these 8 bits are stored in the RX data. After that, a stop bit is used to confirm the completion of data reception. If data is successfully received, then the valid RS is asserted high to indicate valid data availability. After that, we will see the timing diagram of receiving module. Basically, in timing diagram, I have shown the baud rate counter, shift, bit counter, RX data, and valid RX. At the time being, the baud rate counter, it is mentioning 5208 and from where it comes. So it has some calculation part. So next, we will thoroughly analyze this timing diagram and the working of the receiver module. Now we will see some calculation part to validate the timing diagram. So first of all, baud rate counter. So before going to the baud rate counter, first see what does baud rate mean. Baud rate of 9600, what does it mean? Basically, baud rate means the number of bits per second. So baud rate of 9600 means 9600 bits per second. Then what will be the bit time? That is the time for one bit. So bit time can be calculated as bit time is equal to 1 divided by baud rate, and as the baud rate in our case is 9600, so the bit timing will be 1 by 9600. It comes out to be approx 104 microsecond. So this is our bit timing. Now what is the number of clock cycles per bit? Since the FPGA clock that we are using is FPGA clock, it is 50 megahertz. So the number of clock cycles per bit will be clock divided by baud rate. So your clock frequency is 50 megahertz and baud rate is 9600. So it comes out to be, on calculation, it comes out to be 5208 approx. So we need an integer value, so I have rounded to 5208. So in UART receiver, a baud rate counter will count the clock cycle until it reaches 5208. And when the counter hits 5208, it resets and the UART samples the next bit. So from the timing diagram, we can say that when the baud rate counter reaches 5208, then the UART samples the next bit. And for the clock to count up to 5208, the number of bits required is, it can be, we can determine it by taking the log to 5200. From there, here we can determine the number of bits required, and then we will use it in our Verilog. Now we will see sample counter in our UART receiver. Sample counter. Sample counter is used to ensure that the UART receiver samples the incoming data at the correct point within each bit period. Basically, our baud rate counter counts from 0 to 5208. So the UART receiver typically samples each bit multiple times. So in between 0 to 5208, our bits are sampled multiple times, which is commonly 16 times or 4 times. Here I am using 4 times sampling. So within a bit period, the sampling is done. So what will be the bit counter clock cycles? That is, since the baud rate counter counts up to 5208, the sample counter increments every how much cycle? So as we are using sample by 4, so sample counter increments every 1302 cycles. So we basically in between 0 to 5208, 4 times sampling will be done. So here first of all, sample counter will count from 1302, 0 to 1302. Again it resets to 0 after reaching it, then again 0 to again. So 4 times sampling will be done. So we are done with the baud rate counter and the sample counter, and now we will see the bit counter. Bit counter basically counts the number of bits. Since the number of bits are 10 including the start bit and stop bit, so when the when number of bits become 10, bit counter resets to 0. So bit counter basically counts from 0 to 9. So when the number of bits become 10, bit counter gets resets to 0, indicating that the 10 bits are reset. And after that, the valid signal sets high after receiving the 10 bits. And the sampling of each data is done at the middle of the bit period, and after sampling, the bits are moved to the RX data. So we have seen the basic calculation here. Now we will see the Verilog code and verification through test bench implementing this law. Now we will see the Verilog code for UART receiver. I am using Vivado for simulation and synthesis purpose. So this is my module name, and these are the input and output ports that we have used in our design. We have already seen it from the block diagram. After that, these are internal variables shift for triggering the shifting of data at the middle of the bit period. After that, state, next state for state logic, FSM logic. Then is bit counter. We have already seen the bit counters count from 0 to 9. So its size is 3 down to 0. Then it is sample counter. As we are sampling data 4 times, so the size of sample counter is 1 down to 0. We have already seen the baud rate counter. It is basically 14-bit value, so its size is 13 down to 0. RX shifts register 10-bit data. It will store the 10-bit data. After that, clear bit counter, increment sample counter, clear sample counter. These are the parameters of our design. After that, UART receiver logic. At the positive edge of the clock, when the reset is applied, the state, bit counter, baud rate all gets reset to 0. And in the else part, the baud rate counter will increase and it will count up to 5208. And if the baud rate counter is greater than equal to diff counter, what is diff counter? Diff counter is basically the sample counter that we have seen. So when the baud rate counter is greater than equal to diff counter, then the baud rate counter will reset to 0 and the state will change to next state. That is sampling of, if the counter reaches the baud rate with sampling, then reset the counter and the valid RX is set high. And if a reset is applied, then in the shift register, which is 10-bit, the RxD, which is the input pin, is asserted and it will load the receiving data. So these are clear sample logic, increment sample, and clear bit logic. After that, these are state machine logic at the positive edge of the clock. Here shift is 0, we are initializing our internal logics. After that, if the state is in the 0 state, we are using 2 state, 0 and 1, ideal state and receiving state. So if RxD is 1, then it will remain in this state, because to start the transfer, the RxD should be low, because the start weight should be low, then the transfer will start. And else, if the RxD is low, then the state will change to receiving state and the clear bit counters, clear sample counter sets to low. And in the next state, the sampling counter when equals to the mid sample, then the shifting will happen. So these are the logic that we have already discussed. So this is the Verilog code of our UART receiver. Next we will see the test bench code and verify it from the waveform. Let's see the test bench of our UART receiver. So these are clock reset RxD, RX data. And here instantiation of UART receiver is done. Clock generation logic. Now this is the task which is used to transmit the UART byte, that is 1 start plus 8 data plus 1 stop. And this is the logic. We have already discussed what is the logic behind this. This is the baud period. We have already calculated it around, it comes out to be around 104 microseconds. We are using it. And this is the initial begin logic. We are initializing our signals. After that, the main component of the testament is that we are reading from a file string.txt. So we are writing a string in the string.txt file. After that, we are printing the character, we are transmitting the character via UART, and then after that we are obtaining the output where UART correctly transfers the character and gives the proper result or not. So this is the logic behind this. Next we will see the waveform and we'll test whether our design is working properly or not. Now we will see the test bench verification of our UART receiver module. Here we are using file operation in C to pass a string to our UART receiver test bench. So we are using a C program to write a string to a text file. So basically a C program creates a file named textfile.txt in write mode and it writes the string. For example, here we are writing a string and after that it closes the file to save the changes. Now our Verilog test bench read this file character by character and transmit it over UART. So basically how the flow goes, our test bench opens the file which contain the string that we will write here. After that it will read the characters one by one. It will print each character for debugging purpose and it will send each character over UART. After that it closes the file when done. And after that each character is transmitted as a UART frame. So start bit, it will transmitted like start bit, data bit and stop bit. After that the Verilog receiver module will sample the RxD at the correct baud rate. It will detect the start bit, store the receive bit into RxD and raises a flag when the data is valid. So let's write some string here. First compile it. Let's say I am writing Anurag here. So this Anurag gets written in my text file.txt. So from the Verilog test bench, I will call this text file.txt and transmit it over the UART receiver module. So let's see the waveform and analyze it from there. Now we will open text file.txt in our receiver module. In this file, the string Anurag has been written. So basically it will read character from the file and will send the character over UART. Now let's see the working from the waveform. Here the character, these are the characters which it read from the file. So 41 is basically the ASCII value of A, capital A. This is the ASCII value of N, A, N, ASCII value of U, R, A, G. So here we see that the RX data correctly displays the expected value in the simulation. Here 41 is displayed, which is the ASCII value of A, 6E, which is the ASCII value of N, after that U, R, A, G. So here we can conclude that the UART receiver is successfully detecting the start bit, reading data bits, and after that detecting the stop bit. When the stop bit is detected, it correctly displays the character which it read from the file. So the transmitted data from the file is correctly received by the UART receiver without error. So it shows that the UART sampling and bit alignment are correct, and if there were timing issues, then it would display garbage value instead of the expected ASCII value. So no data loss or corruption happens. So we can say that our UART receiver is working fine. So this concludes our stage 1 of project development. Now we will move to stage 2, in which we will see the C programming code for transmitting the string over FPGA. So for that case, the knowledge of API, application processing interface, and how that programming is different from the normal C programming, we will see that. So the stage 1 of project development, which is UART receiver design and verification, has been done. Now we will move to the stage 2, which is C program for UART transmission. So the first step is serial port communication setup. On Windows, we use the Windows API to access the COM port, which allows the communication between PC and the FPGA. The key configuration include baud rate setting, data bit, stop bit. So these settings must match the FPGA's UART configuration. Since the baud rate on which we are working is 9600 and data bit is 8 bit and stop bit is 1 bit. So these settings must be done. Next step is character input and transmission. After setting up the serial port, the program takes user input. This is done using scanf in C. The character is then sent to the FPGA using the write file function, which writes data to the serial port. Next step is timeout and flow control. Now the question is, why is timeout important? In real-time communication, delays might occur due to various factors like hardware lag, buffer overflow. So setting timeouts ensure that data is not lost and that communication remains synchronized. So the COM timeout structure in Windows API helps set read and write timeouts. And flow control prevents the data corruption by handling transmission speed mismatches between the PC and the FPGA. Now next step is error handling and verification. In this step, we will check if our COM port opens successfully or not. If the COM port is not free, then it will throw the message invalid handling value. And if the COM port is free, then it will execute properly. And the last step is resource management. After transmission, the serial port must be closed to free the system resources. Close handle function is used to properly terminate the communication. So this is the stage 2 of our project development. Now we will see the C program. Now we will see the C program for character transmission. Here, first of all, we are including the header windows.h. Since the windows.header file is an essential part of Windows API. Now the question is why we are using this header file. As in the normal C program, we don't use this header file. Since the program interacts with hardware, which is COM port, we need functions from the Windows API, which is Application Programming Interface. The standard C library does not include functions for serial communication, so we must use Windows-specific system calls. Now the key Windows API functions used in the program are like create file, which opens the serial port for communication, get COM state. Here we are using get COM state. It reads the current serial port configuration. And after that set COM state, it sets the baud rate, data rate and parity and stop bits. After that set COM timeouts, it configures the timeout. Here set COM timeouts, so it configures the timeout for reliable UART transmission. We are also using a write file. Where is write file? Here we are using the write file to send data through the serial port. And also we are using the API, which is close handle. It closes the COM port to release system resources. Now let's break down the API's function in the program. Here the opening of the serial port is done. In my case the COM port is COM6. You can check your COM port through the device manager here. After that generic write means we only want to send data, not read. Open existing which ensures we are accessing an existing port. And if H serial is invalid handle value, it means the COM port is not open. Let's say COM port is accessed by some other applications, then the C program is not able to open it and it will throw the error unable to open the COM port. Next step is configuring the serial port. So here we are using the APIs like these get COM state, set COM state to set our baud rate, byte size, parity and stop bits. After that we are setting the timeouts. Earlier we had seen why timeouts are important. Next is we are sending the data via UART. Here we are using the write file and printf methods. After that we are closing the serial port using the close handle. So this is the basic program for sending a character through C. Now let's compile it and check. Here it compiles successfully. Means our C program is working well. Now once the stage 3 is done, we will pass the character and will check whether the FPGA is correctly displaying or not. Till now we had completed stage 1 and stage 2 of our project development. Now we will see our stage 3, which is final implementation and LCD display. So here first of all we will see LCD display logic, how the interfacing of LCD and FPGA should be done. For correct character display on LCD, we will also see FPGA pin mapping. After that we will see the final functionality by displaying the characters sent from C on an LCD. So let's start. This is our LCD display module. It is designed to display a UART received character on an LCD interfaced with an FPGA. Here we have clock signal, which is FPGA system clock, RX data, single ASCII character from UART, LCD E, LCD RS, which is enable signal and registered select signal, and data line, which is going to the LCD. After that we have LCD command initialization array. These are initial command sent to set up the LCD correctly. After that we have the character received via UART is stored here. Now basically how it works. After power on, initialization command are set one by one. After initialization, the RX data from UART is written to the LCD. It continuously loops through these 7 steps, 6 command instruction and 1 user instruction. So this is the Verilog code for LCD display. Here we have our top module. In the top module, we have instantiated our UART receiver and LCD display. Now we will do the pin mapping. Before doing pin mapping, first of all go under project summary section and select the correct FPGA board. After selecting it, open elaborated design. Here our elaborated design is opened. Now we will do the pin mapping as per our FPGA board manual. So the FPGA board that we are using here is SPARTAN 7. So here the pin mapping of our port is done. After doing the pin mapping, we will generate the constraint file. Here the constraint file is generated. This one. After generating the constraint file, we will run synthesis, and after that we will run implementation. After running the implementation, we will generate the bit stream. Now we will program our device. So here our FPGA board correctly gets programmed. Now we will see the character that we want to display on our FPGA board. So we will go to our C program for character transmission. So first compile our C program. Now let's say I am sending character A. So here in our FPGA board, it is correctly displaying character A. Now again running it for different values. Let's say character G. Again try some other values. Let's say character R. So here character R is correctly displayed on our FPGA board. So we can conclude that our FPGA board is correctly displaying the character that we sent from our C program, implementing final end-to-end project on the data transmission from C program to the LCD via FPGA. Now we come to an end of our project. Through this project, we covered successful UART communication, hardware implementation on FPGA, efficient data handling, testing and debugging. Some of the key takeaways of the project is learning about serial communication, FPGA interfacing, and debugging technique. Similarly, we could expand our project to complete string processing on FPGA. That's all from my side. Thank you for your time and attention.